let us move on to life cycle assessment. We left off last time talking about the general components of a life cycle assessment. There are many models. There are many flavors of how you can assess the feasibility and sustainability and the economics of any technology, any device, any materials, but it always involves looking at the raw material sourcing all the way to the device production. And it also can include labor costs. You have to train a new workforce. Do you have to develop or install or invent new manufacturing capabilities? It includes all of that. That all gets lumped into what people refer to as LCA. We'll do some examples where we take these things into account. But when you read about LCA, you will see there are many, many flavors of how people compute, which is also why when people report on different models of, do we have 6 years? Do we have 10 years? Before there's irreversible climate change effects, it's all based on, different models, but so there is, some range that you'll see, but typically people try to be as transparent and quantitative, as possible. So for the next few examples, we'll talk about hydrogen oxygen fuel cells. So the first step, when we talk about hydrogen oxygen fuel cells is the obvious. Where's the hydrogen going to come from, right? How are we going to refine hydrogen, or how are we going to convert hydrogen from fuel sources that we already have? So one of them could be methane, but if you feed in methane, then you need a reformer. So we talked very briefly about steam reforming. So that means you inject H2O in the gaseous phase, and it will react and produce carbon monoxide and hydrogen. And then you can do the water gas shift reaction to convert the CO into CO2 and produce more hydrogen. So basically, it can be this cascade of reactions. But what you need to map out is, okay, I have some source of methane. I'm going to pump it in. I'm going to then steam generate it. You have some sort of preheater, then you have the fuel reformer, then you have water gas shift reaction. Then you can produce your your byproduct. H2, N2, CO, CO2, more steam, you clean it up, and then you input hydrogen. And then what you can get out of the fuel cell is, H2O, your anode exhaust can also have vapor in it, and then, yada, yada, yada. So you could see, it's quite a process. So it's not just, the LCA is not just, okay, we're going to put in hydrogen. It starts well before we put in hydrogen. Where does our hydrogen come from? And is the method of making hydrogen as intensive in terms of the energy input, or is it better in some way? Does it cost less than, let's say, extracting gasoline from fossil fuels and then refining it to remove the sulfur, like all of that. So it's not as plain and simple as, well, obviously hydrogen oxygen fuel cells do not emit as much CO2 as gasoline, gasoline powered vehicles. So fuel cell vehicles must then be better in terms of emission. That's not always true, okay? Because the sourcing of your hydrogen can start to negate some of the emissions at the for the end product. So part of the LCA, you also need to talk about efficiency of your device, right? So if your argument back in the day for internal combustion engine, well, you can say, well, it's still more efficient than having a horse, right? Burning gasoline is 16% efficient. So, well, 16, maybe a little bit more, maybe 20% efficient. So that's a pretty low number, but it's still more efficient than feeding a horse and then, raising in and yada, yada, okay? So that's a very hyperbolic example, but then we do the same thing for fuel cells. We say, okay, how efficient is a fuel cell? If I input hydrogen and I input oxygen or I input air to get the product, how efficient is this reaction? So the efficiency is defined as the delta G divided by the delta H. And we calculated what the delta G of the reaction is, right? We looked at the table, and so we said, okay, so back in lecture 23, slide 14, we looked at the data table and we said, well, we can look up the Gibbs free energy and the enthalpy, and we can calculate, well, delta G is just G of the products minus the reactants. So we looked that up, we did the math, and we said, okay, delta G was this negative 237 kilojoules per mole. We can also do the same for enthalpy. We look it up and we say, okay, well, products minus reactants is negative 285 kilojoules per mole for the product being H2O in the liquid state. The enthalpy would be different if your product were H2O in the gaseous state. So we can also look up that value. And so that comes out to negative 241. So depending on what your product, which phase your product is in, you have what's called a higher heating value or a lower heating value for your delta H. So this HHV is a term that people are going to refer to again and again and again, because the HHV, the enthalpy of formation, right? How much energy does it take to form this product, right? That's literally the energy of the bonds, the H2O bonds in the liquid state and in the gaseous state. So there's HHV and LHV. Okay. And typically people go with the higher heating value, because then if you can manufacture and produce something with lower heating value, then basically it's easier. So you calculate based on what's harder to make, the higher heating value. Okay. So we have the HHV for producing H2O in the liquid state. So it's going to come into play later when you calculate and try to compare fuel cells to internal combustion engine. So the second step is to quantify environmental impacts of energy and related and materials changes. So what that means is, okay, so we're going to input hydrogen. Where are we going to get the hydrogen from? Well, the energy comes from, first you have to, let's say, explore where you're going to get this methane. Is it going to come from the ground? Is it going to come from your landfill? Is it going to come from cattle farming? You're going to extract methane that way. Where is it going to come from? So you do the exploration. Let's say it comes from natural gas. Okay, that's fine. Now you have to go to the field and get that natural gas, right? You have to extract it. Then you have to store that natural gas, and you might have some leakage. So now you've extracted methane from the ground, but when you store it, there could be some methane leak, and there will be some methane leak. So now you're emitting methane, which is even more detrimental than CO2 emission in terms of the global warming potential. And then you have to process that natural gas, and then you pump it through the pipeline transmission, and then you can have, then you feed it into your processing unit to convert it to hydrogen. And then once you get hydrogen, you have to compress the hydrogen somehow, right? You have to put it into tanks and that's pressurized. And then you have to store that for a while. So you need some space to store all of these tanks. And then it gets pumped into a fuel cell. Okay. So that so far is part of the life cycle assessment of, like, where are your inputs even going to come from? Where is it going to be sourced from? So you can treat this very similarly if you were looking, so not at the fuel itself, but if you were treating this and saying, okay, where is my platinum going to come from? Which ore am I going to mine from? And if I'm going to mine it, how do I process the ore so that I can get out the platinum? That process takes a lot of energy. So am I emitting more CO2 and other, greenhouse gas into the atmosphere just to make this fuel cell that is supposedly, going to emit less CO2 than internal combustion engine? Okay, so that's where the life cycle assessment comes in. So here you could see at each step of the way, this chapter has tabulated where you're going to have CH4 leakage, where you're going to have hydrogen leakage, CO2 leakage, emissions. You can also have H2O vapor emissions, which you think, is that important? Because if you emit H2O into the atmosphere, then that's also going to absorb infrared light. That's part of global warming, right? It's that you're trapping in the emitted infrared light, which is what's increasing the temperature of the Earth. Okay, so these are the things you should be concerned about, but there are some similarities. So you think, okay, well, do I have to invent new manufacturing techniques or the way I get the gas out? Not really, because the way we get natural gas to heat our homes and such, this first part, the infrastructure for the first 5 steps is already in place. So for the first 5 steps, extraction of natural gas, refining of natural gas, all that infrastructure is in place. So you don't have to now build new plants. You don't have to train a new workforce. That's all there. The next part, 6 to 9, could be a little different. So if we didn't have hydrogen infrastructure already, and there's a little bit of hydrogen infrastructure, but not a lot, then we would have to invent everything from box 6 and on. So there you'd have to think about, okay, how do I invent a new hydrogen storage tank? Is steel better than carbon composites? Carbon composites are lighter, but how much is it going to cost me to make the carbon composite versus just the steel canisters? Okay, so all of these questions go into life cycle assessment. So here HHV comes in again, because you ask yourself, okay, so what's the most energy intensive part? If I'm inventing something new or I'm working to develop, a process of developing fuel that is going to be, reduced carbon emission, then you look at where is it going to be most energy intensive. So the first 5 part here, the first 5 boxes, it's a total of 10% of the higher heating value. Okay, so where it's really energy intensive is this part, the fuel processing and also the compression. So to get your methane into hydrogen, into usable hydrogen, that is the most energy intensive. The steam reforming is the most energy intensive part. So you would think, well, should I work on that? The answer would be yes, you should work on that. Whereas everything else is like in the weeds. Everything else is pretty minor in terms of energy intensiveness. The other thing is, even though hydrogen compression is only 10% of the HHV, it actually emits a lot of CO2 equivalent. So what I mean by that is, how are you going to compress this hydrogen? Where is the electricity going to come from? It's going to come from your coal-fired power plants that generates electricity now. It doesn't come from another fuel cell. So you can see the conundrum here, right? To make hydrogen and then compress it, you actually have to use current technologies that emit CO2 to produce something that is supposedly, lower emission. So therein lies the problem. So it's not always, well, you should go for and tackle the most energy intensive part of the process, but you also need to think about, okay, well, for hydrogen compression, I need electricity, and statistically, you're going to be using coal-fired plants and it's electricity production to compress your hydrogen, ironically enough. Okay, so should you tackle that? Yeah, maybe, if you can replace all the coal-fired plants. Okay, so then you look and you say, okay, well, how bad is it? All right, what is bad in this case? If we talk about emissions, we can say, okay, so there's going to be some emission, there's going to be some hydrogen emission, maybe methane. Is that worse or in terms of emissions than what the current technology that we have? Then you look up some EPA reports and you say, okay, well, if I have a natural gas steam reformer, the number of kilograms of emission per the number of kilograms of natural gas fuel that you have versus, let's say, coal-fired or coal combustion or natural gas combustion electricity plants, you could see CO2 emission is dramatically lower than if you had natural gas combustion or even coal combustion. So even though you do emit some CO2 to produce the hydrogen, to go get your, natural gas, all that, you could see that it's still much less, like an order of magnitude less than if we keep our current technology, because our current technology is a huge emitter of CO2. What's worse is CH4. So methane has like 100 times more potency in terms of global warming. So the amount of CO2 that's in the air, right? If you have one molecule of CO2, it's going to attract a certain amount of infrared, and then it's going to heat up, okay, the atmosphere. If you have one methane, or you have a 1/100th of the number of molecules of methane as you do CO2, it's still just as bad. Okay, so that means one molecule of methane is 100 times worse than one molecule of CO2 for heat trapping. So that's what's called CO2 equivalent. So it's 100 times more than methane is 100 times more potent than CO2. So even though you see here the emission is lower, these are numbers that are smaller. It doesn't emit as much CH4. That's still, if you multiply that by 100, then you're comparing apples to apples. So CO2 equivalent is something that people talk about a lot. So just because there's not a lot of NOx, there's not a lot of SOx in the atmosphere, it doesn't really matter because the equivalency is what matters. So the global warming potential and the CO2 equivalency is what matters. Then the fourth step is then you analyze the energy and the mass flow in your supply chain. So here's a good example. If we assume that we can replace all of the cars, well, according to 1999 database of the EPA, if we can replace all of the cars that are gasoline powered now with fuel cells, how much hydrogen would we need? And do we have enough hydrogen production to even meet that need, right? If you wanted to stop emissions, we have 10 years. At this rate, we have probably 6 years to cut emissions down by 7.6% a year for 10 years to keep the Earth from warming not more than 1.5 degrees Celsius, right? More than that means there's going to be irreversible climate change effects, as in the glacier will melt and it will never come back, okay? So how do we do that? Can we do it tomorrow? Can we make a whole hydrogen fuel cell fleet tomorrow? Yay or nay? There's a no, Alan?
I think Toyota is trying, so.
Okay,
Yeah.
good for Toyota. Hyundai is also trying.
Okay.
Honda is trying. No, there's actually a number of automotive makers that are trying. But the question is it possible for them to succeed in completely changing out the current fleet that we have, like every single car in the US? Yes, Alan.
So when a gas car pulls to a gas station, the gas station pumps the gasoline from a big tank underneath the gas station, like a gigantic swimming pool, into the car.
Yeah.
If you were to replace all of that system with hydrogen, would it be possible to make a swimming pool sized hydrogen tank underneath every hydrogen station for them to pump out of? Because that's like explosive liquid.
Sure, or you can,
Like gasoline is.
or you can make it modular, as in like you can do the battery swap system. Like if you need a 5 kilogram tank of hydrogen, then we stock 5 kilogram tanks of hydrogen. You drive in, we take out your tank, we put in a new tank for you.
Otherwise, you can create pipeline system.
Sorry, what did you say?
Oh, pipeline system.
You can create a pipeline system. Okay, so these are all great ideas for like what we could do to our infrastructure. But the question is, are we producing enough hydrogen today to completely replace all of the cars that we have that are run on gasoline tomorrow? So if we have like 10 cars on the Earth or in the US, and we want to make now 10 fuel cell based cars. Do we have enough hydrogen to do that? Except it's not 10 cars, it's all of the cars.
In the next 24 hours, absolutely not.
Well, let's say manufacturing is not a problem, right? Let's say human like production of working at a certain rate. Let's say that's not even a problem. The problem is, do you have enough hydrogen? Are you producing enough hydrogen as a country to do that?
I think even compressed and produced, no, but like in the atmosphere also no. I just don't think there's enough hydrogen molecules to power all the vehicles on the road.
So
Like,
your
it's kind
statement
of
is we don't
impossible.
have enough hydrogen.
I honestly don't know anything about the chemical ratios, but I would
Yeah.
just assume that since hydrogen is so dense, or sorry, so
Like,
opposite dense, I mean, it's common as an element, right, that it's very sparse in naturally occurring sources. I don't think there's enough molecules of it.
okay, so Alan says no, because we don't have pure hydrogen molecules. But can you reform methane to make hydrogen molecules? There are enough cattle farms and there's enough landfills out there that we can produce methane until the end of time. Okay, these are the byproducts of these two particular areas. But of course, there's also natural gas deposits. Like we can literally go to Western Pennsylvania and dig up. Now, whether or not we should is another topic, but there are deposits where methane we can dig up something, we can source a precursor to hydrogen. So I have this discussion because this is how you think about life cycle assessment. Before you even think about, is your device better or worse? Do you have enough material to make your device? If you want to revolutionize energy technology, you need to go back to the mines and you need to think, how many mines are there for me to even source my material? Or how many deposits of X do I have to even produce my precursor or whatever fuel I need? So that's what this is. So the mathematical way of going about it, to answering the question and to basically summarize what we talked about, you have to start off with, okay, so how much work do you need? It's going to get done by the current fleet that we have. That means you have to know how many cars there are in the United States, right? So you look up a data table. Someone has tabulated, the EPA has tabulated how many cars exist in the United States. So then you say, okay, well, the mass of gasoline consumed per year in kilograms per year, that's this M, multiplied by the higher heat value of gasoline. So you look this up as well, or you tabulate, you look up the data table, products minus reactants, you get your delta H, okay? And then also the efficiency, right? Just because you have a tank of gasoline doesn't mean you're going to use all the energy that is stored in that tank of gasoline or in that 1 gallon of gasoline, right? It's only 16% efficient. Gasoline, when you burn it, your internal combustion engine, right, only really utilizes about 16, maybe 20% of the energy that is stored in gasoline as a chemical. Okay. So then you say, okay, well, what is the mass of gasoline? Well, that's just the density of gasoline. You look this up, it's about 750 kilograms per cubic meters. You also look up the vehicle travel, the miles traveled per year. So we're talking about a year. So that's according to the EPA, that's on the order of like 10 to the 6 miles. And then I'll divide that by the average mileage of conventional fleets. So how many miles can you go per gallon on average? We're not talking about the most efficient car. We're not talking about the most inefficient car, somewhere in the middle. You take the average. So the EPA also tabulates this information. And then divide that by the volumetric conversion of gallons to meters cubed. So how much space does a gallon of gas take? And then you say, okay, I can do the same thing for fuel cells. The work that is done, the propelled work that's done is the mass of the hydrogen that I'm going to need times it's the formation of that hydrogen. So this higher heating value, HHV, products minus reactants, times the efficiency. So fuel cells, as we calculated, delta G divided by delta H is about 0.83. Okay, so fuel cells are about 83% efficient on average. So then you say, well, that's what I'm looking for. I'm looking for the mass of hydrogen that I need to answer the question, how much hydrogen do I need? And can I replace all the entire current fleet that I have according to 1999 numbers, which obviously we're a few years beyond that. But if we were in 1999, can we replace? So same thing. So if you say, okay, I need to do the same amount of work in fuel cells to replace the current fleet that I have for gasoline. So you put that equal to each other, you move the variables around to get your MH2. So then you basically start filling in and replacing the numbers. So density of gasoline, 750 kilograms per cubic meters. The higher heating value is 47.3 megajoules per kilogram. Efficiency of gasoline is 0.16 in this particular model. You can change it to 20% to see how much farther you can get. How many miles traveled in a year? 2.68 times 10 to the 13 miles. These are numbers that one can look up. You know, obviously I don't know these numbers, but the EPA tabulates all these numbers. The average mileage of a conventional fleet is 17 miles per gallon. So you think, oh my gosh, no, my Honda Civic, you know, I can get away with 38 miles per gallon. That's great. This is not the average. Right. So then the volumetric conversion, 264 gallons per cubic meter. HHV of hydrogen is 142 megajoules per kilogram. So before we had megajoules per mole, sorry, we had kilojoules per mole. This is now per kilogram. So we've already divided by the density of hydrogen to get kilograms. Sorry, not density, and molecular weight. And then in this particular example, it's actually 41% efficient for a fuel cell. I said 0.83 before, but this particular model was 41%. So then you say, okay, that means I need 5.71 times 10 to the 10 kilograms of hydrogen produced in a year to replace my entire current fleet of gasoline cars or diesel car to hydrogen fuel cell. Okay, so that's 57 megaton. Now, a ton, T-O-N-N-E, is different than a ton, T-O-N. Okay, so these two things, one is metric. Metric ton is a ton, whereas imperial, that's just a ton, or a British long ton. Oh my God. Anyway, so 1 ton, this ton is imperial, and that's 2,000 pounds. That's probably the ton that you're more used to. This ton is metric. That's equivalent to 2,204 pounds. So it's actually slightly different. So 1 metric ton or 1 ton, T-O-N-N-E, is actually 1,000 kilograms. So it's totally different, right? Don't mix it up, because then you'll be like NASA, and then your Mars satellite will never make it to Mars, okay? Because you didn't convert metric versus imperial. So there is a difference, okay? So this MT is megaton, T-O-N-N-E, okay? So it is different. Oh my, okay. I guess we'll have to pick up here and talk about LCA step number 5, which is quantifying the environmental impact of the net flow. So we've talked about, fun fact, the US currently produces 10 million tons. So the answer is no, you need 57 million tons. So that's the answer. No, we don't have enough for tomorrow, but over like 5 years, we could. So, yeah. Yeah, so all right. So